So in this video, I'm going to describe the several forms of gravitational energy and how it's applied to the simple problem of dropping a rather small ball from some height. So we start off with a picture. Let's imagine we're standing up on a building, and this building is, let's say, 50 meters high. We're standing up on top, and we drop a ball. Okay, and I'm going to say that the mass of the ball, and I'll use this throughout, is 0.3 kilograms. Okay, I'm going to put the units in brackets wherever I can, and so that's actually so it's clear. So when we talk about an energy formulation, what we always do is we always say something like, let's say we have gravitational energy and we have kinetic energy, and at the very top we have no kinetic energy, because kinetic energy, if you recall, is 1/2 the mass of whatever we're talking about times the speed squared. And the first form of gravitational energy that I'm going to look at, which is useful near, say, the surface of the Earth, is the mass times 10 joules per kilogram meter times the height that you lift it. And this is the first form that I'm going to look at. So at the very top, we have no kinetic energy because we're simply dropping it. And we have a certain amount of gravitational energy, which is equivalent to the mass, 0.3 kilograms, times 10 joules per kilogram meter, times the height of 50 meters. Okay? And this is equivalent to 150 joules. So at the very top, we have 150 joules of gravitational energy. We have 0 joules of kinetic energy, and so the total energy of the system is 150 joules, and that's true at the very top, and it's true all the way at the very bottom and every spot in between. So at the very bottom, we have this object that's moving at some speed, and we can and at the very bottom here, the gravitational energy is 0 because the height is 0, the h is 0, and then we have the total energy would have to equal 1/2 0.3 kilograms times the speed squared, and this has to equal 150 joules. Now that we have that, we can find the actual speed that this object is going at. We'll just solve for the speed, multiply both sides by 2, and divide by the 0.3 kilograms. I end up with 2 times 150 joules all over 0.3 kilograms. Numerically, this is 90, and then units, we have a joule is a kilogram meter squared per second squared over a kilogram. So then I end up with v squared is equal to 90 meters squared per second squared, and then I can take the square root of each of these. That's going to be equivalent to this to the speed, and the units will be meters per second, and the quantity is about 9.49. So we can figure out the speed of the object from conservation of energy. Now, another form of gravitational energy, and I'm going to write it as GE near, no, not near, but GE, interacting with the Earth, is the following: m times 10 joules per kilogram meter times h times the following quantity, Re over Re plus h. So the Re in this case is the radius of the Earth. So the radius of the Earth is about 6,400 kilometers. So this will be about 6.4 times 10 to the 6 meters, and that's the Re that we're talking about. Just for convenience, occasionally I will write this conversion factor, this 10 joules per kilogram meter, I'll write that as lowercase g. And that's just a terminology kind of notation. So one of the things that you may notice is the second form of energy is a lot messier. It has this extra bit, but it's identical to the other one in up until that point, which means the only way it differs is this term. So if we're looking at the total gravitational energy in the second form with the height at 50 meters, so we should come up with something around 150 joules. What we'll have is 150 joules times this quantity, which is the radius of the Earth, so 6.4 times 10 to the 6 meters over 6.4 times 10 to the 6 meters plus 50 meters. So we have the plus 50 meters in the denominator there. Okay, this translates to 150 joules times, and we have to go out many decimal places in this one, 0.199992. So it is almost equal to 1, and it really translates to a difference of about 0.001 joule, so 1,000th of a joule difference in 50 meters. That really is completely negligible when we on all problems. So what we have is near the surface of the Earth, we have these two forms of gravitational energy give numerically identical results. I mean, practically identical. But let's do a different thing. So let's look at a slightly different thing where essentially instead of a building, I go up in a plane and I have the Earth. And let's imagine I go up so high. So I have, this is the radius of the Earth. And let's imagine that I drop my ball from another radius of the Earth. So I get out, so this is that distance as well. So my height is also a radius of the Earth in this case. So my height is about 6.4 times 10 to the 6 meters. And then I drop the 0.3 kilogram mass from that height. How do they differ? Well, if I look at the first form, so gravitational energy near the surface of the Earth, and notice we are not anywhere close to the surface of the Earth, I end up with 0.3 kilograms times the 10 joules per kilogram meter, so that G, times the height, which is 6.4 times 10 to the 6 meters, because I brought this ball up that high. All right. So that turns into about 1.9 times 10 to the 7 joules. Okay. The other form, gravitational energy, by the Earth, we have exactly the same thing. So we still have 1.9 times 10 to the 7 joules, but I'm multiplying by a radius of the Earth over the radius of the Earth times the height, plus the height. And this term is, if the height is exactly a radius of the Earth, this term just turns into a half. So I end up with a half times the 1.9 times 10 to the 7 joules. So it takes less energy, essentially. And experimentally, we can actually determine which of these two forms is correct, and it turns out that the second form, although mathematically a little bit less convenient, is the correct form. Now, we use the first form when we're near the surface of the Earth because it's easier. And that's really the only reason that you would use it, is because it's easier. And so near the and they give the same result near the surface of the Earth, so use the easier one. But when you get far enough away, so when your height is a significant fraction of the radius of the Earth or beyond, then you have to use the second form, or else you will overestimate the amount of energy it takes to lift an object that high. Now, one thing you might notice is that, for example, if notice that if the height is 1 radius of the Earth, it takes half the amount of energy as the approximate form would have you believe. If it's twice the radius of the Earth, then I'm at a third, and so on. So it takes less and less energy as I lift this thing up, and so then the speed itself would be lower than it would otherwise be by substantial amounts. Now, in all these cases, we can the gravitational energy has been a positive quantity, and the reason is that we've been taking h to be the height from the surface. But is it possible for the gravitational energy to be negative? And in fact, that is quite easy to do, even in the approximate form. So let's go back to the building. Okay, so we have this building that I'm dropping the ball off of, and I'm going to stand here. Okay, and I said this distance here was 50 meters, and I'm dropping my ball down. Okay, but imagine that this building is really at the bottom of the Grand Canyon or some other thing. So height equals 0 meters is way up here, and let's imagine that this is, let's say, 200 meters down. I'm dropping my ball. I can still do gravitational energy and kinetic energy at points 1 and point 2. But in this case, what I have is I have the 0.3 kilograms times the 10 joules per kilogram meter. All right. Times, we're starting off at negative 200 meters. And that is going to translate to a certain number. It'd be negative 2,000 times 0.3. So it's going to be somewhere around negative 650 or so joules. We go down here, and this is our 0.2. What we have is 0.3 kilograms times 10 joules per kilogram meter times a negative 250 meters. So I've fallen that much. Okay, this is going to translate to somewhere be a lower number negatively, essentially. So what we're going to end up with about negative 800 joules. Okay. And so that's at 0.1, 0.2. We have kinetic energy, which is probably better to put over here in this column, so I'll get rid of that one. So if I have the kinetic energy over here, we have 0, and we have some kinetic energy that I want to calculate. Notice that the total here is negative 650 joules. And that means the total down here is negative 650 joules. And so when I look at this and I end up with a negative 800 joules on this side, I can bring it over to the right hand side, and I get the kinetic energy is equal to 150 joules, positive. Kinetic energy always has to be positive. And notice this is exactly the same thing as we got before. So changing our 0 point doesn't make any difference, because we are always looking at differences between one point and another point. And when we take the differences, the 0 point disappears, and we don't need to look at that. So let's go back and look at one of the consequences of the form of gravitational energy that includes the radius of the Earth. So again, I'll have this picture. We have the radius of the Earth here. and I have a ball that I'm going to throw at some speed. I'm going to give it some kinetic energy related to its mass and its speed. And if the gravitational energy around the Earth is the mass of the object times 10 joules per kilogram meter times the height times the quantity radius of the Earth over radius of the Earth plus h. I'm actually going to rewrite this part of it as simply m times g times h, so that where the g is this conversion factor, just because it makes it more convenient just to write it more rapidly. Okay, so if we have that form and we compare it to the approximate form of say gravitational energy near the surface of the Earth, which is m times g times h, we can ask the question, how much energy that you need to throw the ball an infinite distance? Or in other words, h going to infinity. Okay? In the first form, where you have just mass times g times h, that would be an infinite. I mean, you cannot provide that much. There's not enough energy in the universe to throw a ball an infinite distance. However, that's only the approximate form and only works near the surface. So if we look at the one by the Earth and we have this extra term, we ask ourselves, what happens to this? What happens to the gravitational energy around the Earth as the height gets really, really, really big? Okay? So what happens? Well, as h gets really, really big, the bottom term here becomes very close to h, because as h gets really, really big, it dwarfs this radius of the Earth. And so we end up with is something like the following. We end up with mass times g times h times the radius of the Earth on the numerator all over h. Notice the h's cancel, and I end up with m times g times radius of the Earth, and this means that it takes a finite amount of energy to throw a ball an infinite distance. How much is that energy? Well, we can simply calculate that as the mass, let's say 0.3 kilograms from before. We have 10 joules per kilogram meter. That's our gravitational energy conversion factor there. And then we have the radius of the Earth, which is about 6.4 times 10 to the 6 meters. And this gives rise to about 1.9 times 10 to the 7 joules. Now we can also ask, so that's, given a 0.3 kilogram mass, that's how much energy it would be to throw it infinitely. We can ask how fast that would be, in which case I can say 1/2 times 0.3 kilograms times the speed squared, this is just the kinetic energy, is equal to 1.9 times 10 to the 7 joules. And solving it just like before with the square root, we end up with the speed is equal to about 11,000 meters per second, or about 22,000 miles an hour. And this is what's called the escape speed, and it is actually the speed that you need to escape the influence of the Earth's orbit and Earth's gravity, and to be able to leave the Earth. And you can give that amount of energy. So NASA needs to know these numbers in order to send rockets. So this is one of the consequences of this form of energy, that it has a finite amount to actually throw it infinitely. Okay, now I'm going to introduce one final form of gravitational energy, which is the messiest of them all. But if we learned our lesson from the first one, we basically have the following. We choose the simplest form to use that we can get away with the problems we're interested in. So, for example, if we're near the surface of the Earth, we use the gravitational energy equation for the near the surface of the Earth. It's approximate, and we have to keep in mind that if we somehow switch from that to a problem where we're dropping something from, let's say, the distance of the moon, then we'd have a big problem. We can't use the approximate form near the surface because we're nowhere near the surface. So we can use the next one, the one that is, for, let's say, that allows us to talk about dropping things from much, much farther away. The problem with that equation, as I've written it, even though it looks a lot closer to the approximate form for the surface of the Earth, doesn't work on other planets for two reasons. There are two terms that come into play that will not work on another planet. One is obviously the radius of the Earth comes into both of the comes in twice here, but the other one is this what's called the gravitational acceleration, or I've called it the kind of gravitational energy conversion factor. Whatever you feel like calling it, that is specific to the Earth, and so one would have to look at that. In order to look at that, we need to look at a form of gravitational energy that is a lot messier, and then we will be able to compare them. It is, in fact, near the Earth, in fact, equivalent to the gravitational energy of the Earth equation that I just pointed out. So let me write all three forms now that we're looking at. We have the following: we have gravitational energy near the surface of the Earth is m times little g times h, and again, where little g is 10 joules per kilogram meter. Okay, the gravitational energy not near the surface of the Earth, but will work near the surface of the Earth, is m times g times h times radius of the Earth over radius of the Earth plus h. Again, where the radius of the Earth is equal to 6.4 times 10 to the 6 meters. The final form that I'm going to look at, which is really the general form, is the following, and it looks messier and it doesn't look anything like the other ones. Minus capital G m1 m2 over little r, and this requires a picture. So there's my m1, here's my m2, and the distance between their centers is little r. The big G is a constant, and is 6.7 times 10 to the negative 11 joule meter per kilogram squared. Okay, so that's the units of that constant. So, in the case of near the Earth, we can imagine m1 is the Earth, and m2 is whatever you happen to be dropping. Notice there's this funny little minus sign in the gravitational energy, but it becomes clear when we look at it, in the following way. Let's go look at the surface of the Earth equation. As h goes up, the gravitational energy goes up, which means it takes energy to lift an object away from the Earth. Okay, and that makes sense. Gravitational energy of the Earth, the more detailed equation, when h goes up, the gravitational energy goes up. Again, it doesn't go up as quickly as the approximate version, but it does go up. It has the right directionality. If we look at the new case, as we increase the distance between the two objects, which is the same as saying we're increasing h if we're on the surface of a planet, notice what happens. So if r goes up, 1 over r is going to go down. But negative 1 over r will go up. It'll become less and less negative. And so this energy does still have the right form. Separating objects takes energy. Bringing objects together, you gain energy. You can provide energy. This is what powers grandfather clocks. They have falling weights that slowly drive the mechanism to overcome things like friction and so on. So the direction is correct. However, the calculation is a lot messier. And let me point it out by the same example we did before, and you will understand why we like to use the form, the simplest form when we're talking about things near the surface of the Earth. So I have my building, okay, and it is, say, 50 meters from the ground.